All right. So in the next probably 40 minutes, we're going to set up a little bit different perspective on control systems. So far, we've just looked at the Laplace domain. We can also look at these in the time domain. Like our input shipment work's been in the time domain. We're going to look at feedback control in the time domain. And then some advantages that might have for us, and then a few different controllers that utilize that formulation. So we'll take a little bit of time to review to make sure we all understand how we get into the most common time domain representation of system dynamics and the controllers, and then look at a few different control methods that work from that perspective. Okay. So there are some advantages to being in a time domain. The representation we're going to talk about. So again, time domain representations of system dynamics. Okay. What they allow us to do, right? Remember that the Laplace transform that we talked about and worked through is really only valid for linear systems, right? So it's only valid for linear systems. All right, so remember we had to linearize our pendulum system to be able to write the transfer function form of its dynamics. Right. We also see that the Laplace transform, the S domain, the transfer function formulation of equations of motion, or describing our system dynamics, also gets a little bit cumbersome. Or let's say kind of the Laplace domain is also hard to use for multi-input, multi-output systems. Right? That transfer function formulation, right, you're going to write it as that ratio, really wants one output and one input, right? It's really best at single input, single output systems. Right? You can kind of force a multi-input, multi-output system into Laplace, and you have to use more than one transfer function, and it gets kind of messy. Right? I don't like doing it personally. There's some people that really, really like and always want to stay in Laplace domain. I am not one of those people. Okay. So I prefer moving to time domain. So because of these things, so let's look at how we can write our systems in the time domain. This time domain formulation is also going to give us some nice features, right? What's going to allow us to do? We don't have to worry about the system being linear anymore. So time domain, we can start being able to deal with nonlinear systems. We can deal with nonlinear systems in their dynamics. We also can deal with kind of a type of nonlinearity, but a really common one, kind of varying parameter systems. So I have some parameter in my system that's not one of the states of the system, not how it's moving, but maybe my spring constant is changing based on temperature or something. It's quite a common case. Right? That's really difficult to do with a pure Laplace formulation. It's really easy for us to do in the time domain. My spring constant or my damping ratio or something about my system is changing with time. So parameter varying systems. It's also going to let us do, in linear case, basically is going to allow us to really leverage our knowledge of linear algebra, right? And you'll see a lot of this time domain control systems work. The mathematics behind why it works and how it works is just linear algebra, effectively. Okay? And the analysis of the dynamics, analysis of the control system is linear algebra. Okay? So I think we have some benefits in the time domain. Okay? Let's talk through how we get there, how we might write a system, set of equations of motion in the time domain through an example. All right. So we're going to talk about a few things. Let's make some definitions. We're going to have what we're going to call the states of our system. Right? And really what they describe for us is the motion of the system. Right? And we'll consider them different, they're not the inputs. And we'll see what that, we'll look at an example in just a second that defines those states for us. Okay. So what we need to define, if we have some system model, let's work a simple example. So I have a mass on a frictionless surface that is attached to the ground with a spring and a damper. All right, so kind of textbook style system, basically. And then we have some external force F on the system that can cause it to move. All right. So I'm going to write the equation of motion for this system. What would be my first step in that? Free body diagram. Good job. Again, I recommend you guys always draw these even for really simple systems like this one. Okay? What forces do I have on this system? Damper and spring. Sure thing. And of course, I also have, just to be complete about it, gravity and the normal force. And because the thing's not moving vertically, we know those will always cancel forever. So we can kind of ignore them. Right. So I can write the equations of motion pretty easily. Like so. What is the force from the spring? Mm-hmm. How about the force from the damper? Cx dot, yeah. So I just substitute those and I can collect terms. So there I have my equation of motion describing this pretty simple system. Seems like most of you know how to do that. That's good. So let's take actually simple, maybe 2 minutes to review. If I wanted to write the transfer function form of this equation of motion, what should I do? Or what is it, maybe? Laplace transform. So I want to take, basically, the Laplace transform of the whole thing. Right. We remember the kind of shortcut we can almost always use for kind of systems we look at. Right. The two derivatives is s squared. So we can write Write that, where capital X is the Laplace transform of x, and capital F is the Laplace transform of that input force. Right? So if we want to write the transfer function form of this, our output is x, right? And our input is f, so we can write x over f. And there we have the kind of Laplace transform version of this system's dynamics. Hopefully that looks familiar. Okay, so there we have kind of there's our Laplace domain solution for this system. Well, I want to write the time domain version. Okay, so let's think about how we need to do that. The first step we're going to do is take our second order differential equation. It describes the dynamics, this guy. And what I want to do is write that as a system of first order differential equations. Okay? So this guy is a second order differential equation. Right? As most equations of motion are going to be, for mechanical systems at least. Okay? And what I want to do is now write that as a system of first order differential equations. To do so, I'm going to have to define some variables that let us do that. Okay? And I'm going to define what we call the state. Define our states in this case, or the state variables. For this system. And you'll often see them defined, they're almost always going to be called X. You'll see in the example code on the website that I have for you guys there, I will call it W just to avoid some confusion, but we'll call it X. So there's going to be some vector X of states, and I'm going to say our states of our system are this X and X dot. Okay? X and X dot are our system states. So this thing by itself, we say is the state vector, and then these guys are the system states. All right. And what I want to write an equation. Our goal here is to write some function that relates our first derivative of these states to the states themselves, our inputs, and time. Right? And this can be a nonlinear function, or functions, right? It's going to be a system for us. So I want to write, in this case, x dot. Well, let's look at just what that x dot is in terms of our states. Well, if you know x is this, then our taking the total time derivative just gives us that. Okay? And what we said is, well, I want to write that in terms of my system states. Well, let's look at that, what that might be. Well, I have the kind of first row here is x dot. What is that in terms of my system states? Let's actually and you'll see it written, let's do it this way, to clarify. Quite often see these written, once you get it into your state vector, you'll call each state, subscript each state by the number it is. So x1, x2. Right? So if I take the derivative here, I know that derivative of x dot, well, which one of my states is that? It's just x2. Good job. Okay? And then I look at x, my second derivative of my second state is just x double dot. Well, that should look familiar. We can just kind of rewrite this equation to get that one. Right? So let's kind of we just have that. Okay. Now I want to write this in terms of my state, so I know that guy's x1. I know this guy is x2. So now I write the second equation in terms of my states too. And I have an equation in terms of my states and then my input. And now I've taken my second order differential equation that represents the equations of motion and written it as a system of first order differential equations. Okay. And what you'll see, there's a few reasons we do that. One is that we can solve these really efficiently numerically. Right. And pretty much every numerical differential equation solver on the planet is designed to accept first order differential equations, not second order differential equations. The one bundled in MATLAB, ODE 45. The one bundled in my lab uses Python quite a bit. Expect ODE int and ODE are two functions. Expect first order differential equations. So we got to a time domain representation of our equations of motion. We also can kind of simplify this a little bit further. All right. What we can do is write this in what we call state space form. Okay? So I'm going to write this, and I want basically state space form is going to take this and hopefully be able to force it into some kind of matrix form. Right? So I'm going to take my time domain representation, and I want, now my kind of goal is to be able to write this not just as a nonlinear function, be able to write it as a linear function in that form, where A and B are matrices. Right. This form is generally going to require it being linear. So we can have nonlinear equations of motion in the time domain. Once we try to transition into what we call state space form, we're forced again into linearity. We have to linearize our equation of motion to get there. Okay. Well, let's look at how this works out. So in this case, okay, I'm trying to fill in two matrices to force this guy to match that one. Okay. So what, basically we can work one row at a time, let's see. Right? So I have x1 dot is equal to x2. Well, 0, 1. Right? And then there's a 0 over here. There's no f showing up in the x1 equation either. Okay. And I look at the second equation, well, x2 dot is minus k over m times x1 minus c over m times x2 plus 1 over m times f. There we go. Now we have the state space form of this equation in motion, where this matrix is A and that matrix is B. So we have, might as well write the rest of it. Here's the state space form. We'll call this A matrix. You'll see called the state transition matrix. Okay. And we can get, like we could from our transfer function, right? And by looking at this characteristic equation, you actually get a lot of information about this system response just by looking at, let's say, the eigenvalues of this A matrix. And we can do eigenvalue analysis of this A matrix and get some information about how the system will perform. It's quite nice. Okay. So this just describes kind of how the inputs will affect the states. Right? We also can define another matrix equation that will define basically our outputs. So sometimes our outputs are not a direct measure of these states. Right? In this case, I probably could measure x, right? But maybe I could have to measure something else, right? In this case, it's kind of hard to see. But we also can write an output equation, let's say y, with two other matrices. C times our states, and D times my inputs. Okay. So this matrix, we can write some combination of these states to generate some output. Right. Quite often, maybe in simulation, and particularly if you're doing some research work, C is some identity. I want to output every one of my states so that I can measure them and do some analysis for my research work. Right. Quite often you have maybe the position, if you have a robotic arm, let's say. Right. Your system states will probably be the angle of each joint. It's a common way to write the equations of motion. But if I want to write the endpoint location, I know I have to write L times some angle and do the geometry to get the output I need. Right. So I can form some matrix to do that for me. Right? And being able to write it in this form allows us to do some kind of cool operations. Okay. This kind of process we just worked through is exactly the same you would do if you had n different degrees of freedom. In this case, we have just 1 degree of freedom, right? We only have x that we care about. Right? This process, figuring out exactly what we did, works if there's 15 degrees of freedom, even. Right? Gets a little bit more work, but it still works. Still will be fine. Okay? So let's try one of those examples really quickly. And then we'll get back to some control stuff. And we'll leave that up for now. Time domain. Let's do an example. So we'll take the system we had. And add another mass to it, basically. And I think we want a force too. Yeah. Do a force 2. And we'll call the force U this time. Okay, so now I have 2 masses with some springs and things. Right? And then a force on the end. Right? So I want to write the equations of motion of this, and then I want to take those equations of motion and write them in state space form. Because that's our objective in the next few minutes. Okay. So if I want to write the equations of motion of this system, what's my first step? Free body diagram. Yes. We have 2 bodies to worry about. Okay. What forces do I have on M1? So spring and damper there. I have some spring 2 force too. Let's see, how do we want to write that? I'm going to write it in that direction. Okay. If they're in the spring and damper in that direction on M1, what direction are they acting on M2? The other way, right. So we have spring 2 force and damper 2 force acting on both those masses. Okay. I have also U, correct? And I have that guy. And because we're constrained to move just horizontally, we know that the gravity and normal forces for both of these balance, so we get to ignore that. Okay. So let's write the equation of motion for the first mass. Right, we know that it's just the sum of all those forces acting on the guy. What is the first spring force? Yep, K1X1. What's the first damping force? Yep. Okay. What's the second spring force? All right, so we're going to have K2, X1 minus X2. That's right. How about the second damper force? Exactly right. All right. And the way, if you ever, kind of a common point of confusion is what order should those be in sometimes? So I think it can be any order, but it just has to match the arrows. So one way I like to think about it is if I'm working on the X1 equations of motion, is don't move M2 and then start moving X1. In what direction would the force be? Okay. And then, well, if X1 is bigger than X2, it pushes back this way, so it matches our arrow on our free body diagram. That's kind of how I picture those, to make sure I get the order of those components correct. Okay. So we have an equation for X1. X2 is just that, right? We have the spring and damper force, and then the control or the input U. Right? We know these guys already. We already figured them out. So now I have my two equations of motion for my two different degrees of freedom. Good to go. So now I have a system of differential equations to describe the motion of this system. Right? And the system in this case of second order differential equations. Right. So let's write that system. And what I'm going to do is collect some terms to make it maybe easier to see. That's going to be okay. So I have again, I have a system of second order differential equations. And I just collected terms. Hopefully did my algebra right. Okay, so I want to get this into state space form. I want to be able to write this in that like this. Okay. So my first thing I had to do basically is pick out what my states are. Right? So I need to define my state vector. What should my states be? Okay, so I could choose she's proposing I choose that as my state vector. Is that right? Okay. Do I have any other choice? Was that? Yeah, so I could change the order of these however I want. Right. So I could write choose the order to be different. Right? That's actually, I tend to do the second one. That's kind of how I learned it, so that's what I do. Right? But it doesn't matter. Right? Could I choose anything else? Well, I could look at this equation and say, well, what shows up in my equation is x1 by itself, and then always together are kind of x1 and x2. Right? So I could do, maybe, that, if I wanted to. That works too. And in some cases, you might want to do some equations like this. For example, maybe I have a good sensor that is able to tell me x1 minus x2. So I can choose that to be one of my states to make it easy to use that sensor. Okay? So the point that I'm trying to make here is that you have some choice over what your states are going to be. And quite often, making a really smart choice about what the states are can make your system much easier to understand and much easier to control. Okay? So, all right. So I have that. Let's make a little bit more space. I'm going to pick, just to match my notes, let's pick this second one. Okay? But any of them are fine. Any of them are correct. So I want to write, again, I need to write x dot. If I do that, I get that as my kind of time derivative of my state vector. Right. Well, if I'm going to write x1 dot in terms of my state, what state is that? It's just x2, right? There. Okay. If I want to write x1, oh, sorry, there's an x1, I forgot. Yeah, so basically I need to divide this equation by m1, and then I have kind of everything mapped out for me already. Right? So x2 plus So x1, x2, x3, x4. This is why I often will use w instead of x. But I'm leaving saying x here because it's the most common notation you'll see in textbooks and academic papers. Even if your system variables are x's, you'll see the states as x. So make sure you're kind of being neat with your work and keeping track of that. So let me make I have states x1, x2, x3, x4 that are different than x1, x2 here. That can be a little bit confusing. Okay, so if I look at kind of my third state is x2 dot, that's actually my fourth x4. Okay, and I look down at my fourth state is actually x2 double dot. Well, that's just this equation of motion now. Right. So I'm going to, let's see, I'm going to write K2 over M2 X1. And then in this case, I have my input as well. And there we have. I have now a system of first order differential equations for this system. Right. So actually this system is a linear one, right? So I could write this pretty easily now in state space form as well. Let's do that really quickly. And we'll take another short break probably. And there we have our state space form of this equation of motion. Right. So we see this matrix. There's that. We got to the state space form. And now what you'll see is once you have the equation of motion either in this form or in this one, now it's really easy to start using some software and some kind of modern control techniques. We'll say kind of post-space race control techniques. Right? And actually most, for example, the control system toolbox in MATLAB, you can set up the system by just giving it the A matrix. A and B, and well, C and D too. Right? Or you could take this version of the equations of motion and plug them into a differential equation solver. Maybe you have some nonlinearity or something there. Okay. So in the notes, there will actually be one more example of how to do this for you guys. I think we'll skip it for today so we can get to some controls part using this. So actually, let's take a break right now until another 10-minute break, and then we'll finish the last 30 minutes. They've asked me to finish early to make sure you guys can get to lunch today. So we'll try to finish around 12:30 to make sure you get lunch. So back in 10 minutes, and then we'll finish out by 12:30.